Hello, this is my attempt to get this video to a shorter length and a more manageable file size. See if I can get this explained quicker. So, Collatz conjecture. Does it always fall to 1? If it always falls to 1, that means it always hits a power of 2 from an odd positive integer, right? Always will find a power of 2 somewhere or another. Not only that, but the more compound the odd is that we're looking at, and the better off we are at finding different numbers, and we want to be able to get all powers of 2 if possible. For all n, if it's even, you divide n by 2. For all odd, which would be 2n plus 1, right? Or 2k plus 1 or whatever. For this particular bit, for this particular bit for n, right? If we're doing 2k plus 1, the k is the natural numbers, and then the range of that would just be the odds, right? So it starts with 1, can't be 0. All right. And so going to try and do our best to find an algorithm that gets powers of 2 from odd positive integers, and we'll start with the odd numbers, 2k plus 1 for the positive ones, and that's an S, not an R. I just write terribly. 2k minus 1 for the negative, right? Going directive. They'll both generate odd numbers regardless of the direction, but truly if you do like k equals negative, if this is the positive one and then you negate both where k is negative, 1 is negative, and the output is negative, this is how you generate odd negative numbers, right? And same with the 6k coprime theorem thingy, whatever you call it. You can do 6k plus or minus, but if you break it out the same way you do that, you have all positive integers, all negative integers. Where k is starting out with a negative 1, k starting out at 0 minus, and then you go from there, right? So you generate negative numbers when k is negative, and then you negate the y that is the output, and it reflects it properly over the y-axis and keeping it on the same positive scale. Went through all that fast. Anyone that should be able to read a formal paper should be able to understand what I'm doing, because I'm going to have to learn how to do that. So I'm presuming a whole lot here, but please bear with me if I don't do it right? If n equals 2k plus 1, there's all this. And x can be 2x plus 1, there's all sorts of stuff. But anyway, so we've got 6k, we've got several things that go with the powers of 2 when you go with the 6k, right? It's all the powers of 2, all that's not the powers of 2, and all that sort of stuff. So you got a lot of cool odds and evens with the 6k. Everyone's pretty familiar with the 6k plus or minus 1, or 6k plus 1 or plus 5 for the positive coprime. And that's where all the primes are going to be, right? We're not going to start with this one to build our algorithm, because this has a whole lot of primes in it, and that makes it hard to build compound numbers. It would be nice if we could actually avoid these when we're trying to build. So we'll keep that off. If we come back to it, we can come back to it. But for the moment, this is basically where all the primes are, and they're not compound. And a lot of these are even, their factors are prime. So we'll just say that. 6k plus 3 is always going to be an odd number, and they'll never be prime, right? There's odds, and it'll never be prime. You can always at least take a 3 out of this number, so it's a compound odd. That's in our favor. We like that. 6k plus 0, right? The 0 one, the 6k, the multiples of 6. Even, 6 guarantees they're even, but there's also a 3 in there, so there'll never be a power of 2 in these, right? There's no plus to move it to another number, so it's always going to be a power of 6. There's always going to be a factor of 2 and a 3 in here. So this is an even number without 2's, and we want to guarantee we find powers 2. So if we can avoid this, we'll try. And then there's the last two numbers, the 6k plus 2 or 6k plus 4. And those are going to be even with the 6k, and then they move it an even number of spaces to the right. And so those are going to be even. And all powers of 2, since we don't have any other numbers in the positive integers, all positive powers of 2 are going to be within these two numbers, right? So if possible, we'd want to start with the most composite odds, or basically no prime odds, and all the powers of 2. They happen to be real close to each other, which is nice. Right? Real nice bit right there. All right, so now we're going to work with those, right? We want to go from even. If it goes from even down to odd, we want those odds to be of the compound form if possible, so we can work magic with multiplication. And evens are going to be made of these two, and we want to find powers of 2 in there. Let's break these down. Even 6k plus 4, this is take out a power of 2, that's 2 times 3k plus 2, right? So when k is even, this is even. And it's all, and if it's a power of 2, it's going to be a subset of those evens. If it's going to be a power of 2, this is going to be even. So when k is odd, though, we'll look at this real quick. This is, if you divide it by 3, this is 3 times 2k plus 1, which is this, plus 1. If you look over here, this is 6k plus 3. You take out a 3, that's 2k plus 1. So 1 less than that and 1 more than that. This also happens to be 2 times 3k plus 1. Well, if k is always odd, it's also of the function 2k plus 1 or some form of it, right, with a different number than k. So it's of another compound. So this is really just 2 times this when this is odd, but only when this is odd. But when this is odd, this is also even and possibly a power of 2. And this is when you do the same function. This is 3 times 2k plus 1 minus 1, right? So if we're going to take an odd number, we need to see if we can, what happens when we generate. Well, it so happens that when you take 2k plus 1, right, 3 times an odd, and add 1 or subtract 1, you get these numbers. Well, goodness gracious, the multiplication works. But funny little thing, when you start going down, as long as k in this one, right, if you take it out to 6k plus 2, where it's actually 2k plus 1 to get the variable back, then when k is even, this will be this, or I'm sorry, when k is even, this needs to be k needs to be even for this to be odd, and then when k is odd, then this will be even, right? So when k is odd, you'll divide it by 2. When k is even, you'll run into a problem. The odds on this are going to start generating 2x's. And you don't get a power of 2. You get the evens that don't have it. You actually get the opposite. But not only that, now you're picking k's from there, and the x you get over here may or may not be even or odd, but you'll start cycling back. You're only going to get some powers of 2, right? You're only going to get only the ones of these. There'll be the powers of 2 within here too, but you'll miss these. If you do the plus 1 for the odd, right? 3 times an odd number plus 1. 3 times an odd number plus 1, 3 times an odd number plus 1. Well, as long as k is even, you actually will get an even number. 3 times an even number is even plus 2 is another even number, so you won't have to worry about this. When k is odd, it'll look like this. But when k is odd, right, so you see it? K is odd. It'll still get the multiples, it'll still get powers of 2 that are 1 less than this one. Will still be this format here. So this will get all powers of 2. These numbers won't. These numbers never will. The odds never will get powers of 2. The 6k will never have a power of 2. And this is the only function out of the 4 or the 2 that will carry both forms that will require it to be power of 2. There can't be any other form. This is how it has to be by identity. I'm going to have to put that in the paper. I know that's the rules of the prize, but that's my proof and I'm staking my claim. It can't be anything else but positive. And if you flip it around so that you got 2k minus 1, then the 3n minus 1, right? The 6k minus 4, 6k minus 2, this becomes 3 times 2k minus 1, then it flips. Then the minus 1 works for the negatives. You got to, as long as you properly reflect across the y-axis and keep it in the positive, so it stays in the positive y output, then you use the 2k minus 1 and the 6k and the minus, and the exact same logic applies. If I were to represent it here, this would be 6k minus 4 and this would be 6k minus 2. 2k minus 1, 2k minus 1, 2k minus 1. And then this one would be the one that works. The minus 1 would work. And it would be the only one that works for the negative because it's properly reflected across the y-axis. By the identity and the coprime theorem using 6k as the base, this is the only way you can do it with positive integers. And that's why it works. I don't know what's really obvious and what's not. I know it's obvious to me. I hope I can do this better, but I believe anyone that can read a formal paper will understand what I'm saying, hopefully even more. This is Andrew Bounds. That's my Collatz conjecture proof. Thank you.